Okay, hi. So now we're going to go insist on really some of the subjects that Anil touched on. And really what we're concerned in this talk is about how to estimate the performance of your model. Because what we really want, one of the areas where we want to insist when you have pattern recognition is that what matters is how well your model does on data that you haven't seen before. So that's one of the fundamental shifts from when you're doing group studies with a t-test, for example. Here what matters is I want to have an estimate of my generalization ability for my classifier. So that's basically what this talk is about. So I'm going to talk about a bit more about the principles, really a bit more theoretical than what you've seen before. I'm going to spend some time on algorithms that you can use to estimate performance of your classification problem. And then I'll show you a few point estimates of classification performance, because we talk about sensitivity, specificity, negative predictive value, this kind of thing. So we'll talk, there's basically one important matrix that you need to know. And if you know this one, you can compute any stat you want from that. I'll also talk a bit about regression performance for people that are doing things like support vector regression, for example, although that's quite a general part of the talk. And finally, I'll end up with the confidence intervals. How can you trust? I mean, basically, we have point estimates, and now how wide is your confidence boundary about that? If I have time, I'll also touch on how to compare classifiers. If you have two classifiers, how do you know which one is better, and is it statistically significantly better? The data we're dealing with has some specificity, so we can't just use like a simple t-test in this case. Okay, let's start with the principles. So that's overlapping again a bit with Anil's talk, but this is really I think that's really core to understand what we're trying to do in this session. When you're talking about classification, what you're trying to do is you're trying to learn a function. So we noted f. In some areas of pattern recognition, they tend to write it theta to say parameters, so model parameters. For example, it could be a Gaussian mixture model, which you can use as a classifier. So f. And what we have is this function has access to some data, and what we want is to predict a set of discrete labels. So the big set of labels, I'm denoting it capital omega, and the little class labels, they're the little omega, so omega 1 to omega c. The classical example is if you have two classes, let's say you have patients and controls, whatever the disease is, then you would have omega 1 is patient, omega 2 is controls, for example. Okay? And so the function that you have, you can think of this function is basically you can do anything goes. Like it's really, machine learning is whatever function you can imagine that can take a vector from a high dimensional space. Here I'm denoting that RD, D is the dimension of the input. In structural imaging, that would be, for example, the number of voxels that you have in your image. If you're doing connectivity things, that could be the number of edges that you have in your graph. Okay? So it's a real valued vector space of size D, and from that you're trying to project down to, for example, in the case of two-class problem, to just a set of two categories. So that's classification. In regression, again, you're trying to learn a function from a high-dimensional vector space, but this time you're trying to predict a target that is a scalar. So you're going from RD to R1. So basically you can think of these as basically massive ways of reducing the dimensionalities, of taking data, high-dimensional data, and spitting out class labels or spitting out targets. An example from the bottom example for regression, for example, is you give me, I don't know, a resting state connectivity graph, and I tell you the MMS of the person, the mini-mental state examination, for example. That's one of the things you could do with this kind of approach. But in both cases, what this is trying to do is basically approximate a real-world function, capital F, that spits out data. But we don't know what this function is. So there's somewhere in the ideal world, there is a function that generates data. We don't know what it is, and we're trying to approximate it. Okay? So we don't have access to that. The only information we have about the function is the data and the labels that it produces. So since we cannot have access to this ideal function, what we want to do is we have to have an approximate function. And one way that people doing machine learning like to talk about this is they talk about risk. And the risk you're taking when you're doing classification, for example, you're taking the risk of making a wrong prediction. So you're trying to minimize this risk. Okay? Another way to talk about this is to say that you have a loss. So every time you make a wrong prediction, you take a hit. You pay some money, you have a loss. Okay? So that's another way of talking about exactly the same thing. So here, if you look at this function at the bottom, R f of x is 1 over n. the one in the middle, what you have is you define a loss function that, given the real class label for this example, let's say you have a patient, in this case, the associated data xn for this subject, and the prediction from your classifier f of xn, then you want some way of penalizing, of giving away money if this is wrong. So you take a loss if the class label does not correspond to the prediction of the classifier. Okay? And one of the this again, you see that I'm talking about functions in general because you can compute this cost however you want. For example, one of the things you might say is, well, it's very, very bad to make a mistake about a patient. I really don't want to have, false negatives. So let's have very high cost if you misclassify a patient and very cheap if you misclassify a control. So you could do these kind of things. But the most classical way to do this, to define this loss function, is called a 0-1 loss function. And basically, you pay 0 if your prediction is correct, and you pay 1 if your prediction is incorrect. Okay, so if you have this in the back of your mind, so this is really like a lot of kind of theoretical things to end up with a very intuitive thing that if you make a mistake, you pay 1. If it's correct, you pay 0. Okay, but that's by far not the only way of defining cost functions in machine learning. Okay, so this brings us to a very, very important, that's probably, I think, the most important slide of the talk, so I'm going to spend some time on this one. When you have some data and some labels, and you're trying to minimize your risk on this, you're trying to make the minimum errors. Well, the very simple thing to do is you don't model at all, right? You know the labels and you know the data. So if I give you the data point, if I give you the brain scan, you just give me the data. So you don't even have a model, you just have the whole data. But of course you can see immediately that there's something wrong with this picture because then you could predict anything. So that's why you have to really, as Anil was saying, you really have to have into the back of your mind this idea that what we want is to estimate generalization error. Okay? So that's why we always talk about a training set. A training set is where you learn the parameters of your model. If you're talking about support vector machines, you have a few parameters to learn here. Random forest, you also have parameters to learn. Any machine, basically most machines have parameters to learn unless they're maybe like a random classifier. So you can the point here is that you can make your prediction error or you can make your loss arbitrarily small on the training set. So if you look at the screen here, and the bottom, if you look at, let's first talk about the axes here. So on the vertical, oops, sorry, trying not to blind you, John. It's a bit difficult to aim with this thing. Okay, well, let's look at the vertical. I'll be very descriptive. On this box, the left-hand side is the vertical axis. It tells you the prediction error, the error. The higher you are here, the higher prediction error. So you want to be as low as possible, okay? And on the bottom here is the complexity of the model. And you can think of it as the number of parameters in your model. If you're towards the left-hand side, towards the origin, you have low complexity. If you're towards the right-hand side, you have high complexity. So let's first look at the blue /cyan curve that goes down with a little arrow that says training sample. What this says is that if you have given enough parameters, you can make an arbitrarily small error of prediction on your training set, right? So if you just have a training set, if you just have a training data set, just have a bunch of parameters. And indeed, the best model, if that's all you care about, is no model. As I was saying, just make a table of data and labels, and then you can make a very, very, very low. You can actually have 0 error in this case. But that's not what we care about, because what we care about is how well we do on data that we haven't seen. And the U curve that you see, the red U curve, is how well your model does on data that you haven't seen. For example, people that come into the clinic, you want to scan them quickly to see if they're responsive, or you want to see quickly if they have some symptoms, and then you don't know exactly what their diagnosis is in this case. So what the red curve is saying is there's basically a trade-off between how complex your model is and how well you do. That's very intuitive. If your model is too simple, then you're going to make a very bad prediction. You're going to have a high prediction error. You're going to be high on this curve. Think again of the no parameter classifier, which is the coin toss, right? Just toss a coin, and this has 0 parameters. Just toss the coin, and then that's not going to be very good. That's probably going to be random in the limit. Now, as you increase the number of parameters, maybe you learn the mean of each group, right? Let's say you're talking about gray matter density. Now you learn the mean gray matter density, so that's maybe one parameter per person. In this case, what you would have is you would go slightly down, okay? And then you can be tempted to increase and increase and increase the complexity of your model, and at some point you're going to hit the sweet spot where you're just in the bottom of this curve. Of course, you don't know exactly, but there's lots and lots of theory of trying to balance the data fit versus the number of parameters, right? So this is really the core of lots of things in machine learning, balancing data fit versus model parameterization. And if you make too complex, then you can think of it that, of course, if you have too many parameters, then you're maybe going to be very good for the training set, but you're just overfitting. So you're just overfitted. So on the right-hand side of this curve, in a red curve, that's the overfitting regime. Okay, and so this tells us that we need some way of guarding against this overfitting, and the way to do that in machine learning is shown here at the bottom, and this is called regularization. So basically, it's saying that you should not just look at the risk and minimize the risk, but you should also look at the complexity of the model. So here I have this two-term parameter here. So R of fx, the first term of this equation on the right-hand side of the equal sign, this is your risk. This is your empirical risk. It's how well you do on the data. But you also want to balance this with how complex your model is. And the way to denote this is very abstract notation, but it's basically you take some kind of norm of your function that measures somehow the complexity, the number of parameters that you have. And then you have a little tweaking parameter here, lambda. And if lambda is exactly 0, you don't regularize, then basically you can think of this simply as maybe a least squares fit, right? You just care about fitting the model. And if as lambda gets higher and higher, then it becomes more and more costly to have more parameters in your model, and you regularize more and more, right? So you, in Bayesian terms, you could say that you believe your prior more and more for the data that you have at hand. Okay. So that's a very, very generic framework. I just want to pause for a few seconds. If there's any questions, that would be a good time. Otherwise, we'll have a discussion session at the end. Yeah? Yes. Yes, so that would be that's where you want to be, right, on the test sample. So it's really like but you don't, of course, you don't exactly know in advance. You have to try to get to it. So the risk is minimal. The risk on the test set, right? And that's on the test set. Yes. Yeah, so exactly, lambda is so basically lambda will tell you, will kind of correspond roughly to how costly it is to have a complex model along the bottom axis, yeah. Okay. So this leads us to this really important notion of bias, variance, and stability in machine learning. And what we saw before, now we're going to formalize it a little bit more. It's called the bias-variance trade-off. Okay? So if you have a high complexity model, you're going to have very low bias, you're going to have low prediction error, but you're going to have high variance. It's going to be very sensitive to the input sample. Okay, so that's an example. If you have a very simple model, maybe too simple, you're going to have a high bias on the data, so you're not going to predict very well, but it's going to be very stable. So basically, no matter what the data I give you, your model, your prediction is not going to work, is not going to change very much. So here, let's look at three. I just want to show you an example of what this means. So this is a very simple model where you have basically, this is a simple Gaussian mixture model, and we have basically two Gaussians. This is a 2D space. On the top line here, the sigma is the covariance matrix for your data. And you have three different parameterization of this covariance matrix. At the top right is basically just a diagonal covariance matrix that is isotropic. So you have one that the variance is the same in all directions. Okay? So this model, what it's going to do is it's going to basically fit spheres. If you have more than circles. If you have more than 3 dimensions, it's going to fit kind of hyperspheres to your data. And then there's a mean parameter. We don't care about the mean parameter. We just care about the covariance parameter, right? That encodes the distribution of your features between your 2 dimensions in your vector space. Okay, so let's start with this model at the top right. The vertical axis here, D1, D2, D3, corresponds to basically 3 different random instantiation of the data. The data is the red class and the black class. Okay? And these are just 3 random draws from this distribution. Okay? That we don't know. We're trying to approximate it. We're trying to learn it. And the circles that you see, or the ellipses in some cases, these are the model that we're fitting. So let's start with the right column here. So you can see that first, if you fit this isotropic covariance model here, it's basically, as I was saying, it's circle, so it's going to center on the center of mass of each class, okay? And you see that the variance is estimated to be the same. That's D1. Let's look to D2. You see that the model kind of look similar. And now D3, so that's another random draw, another sample from this general population in the world that we don't know. And you see again the model look quite similar. The dashed line in the middle is the decision boundary. So this is the point where if a new point appears and is on the left of this decision boundary, I'm going to say this is black class. So this could be controls. If a point appears on the right side of this decision boundary, I'm going to say this is red class, this is patients. Okay? And you can see that really the important point here is that this decision boundary you see doesn't move very much. So this is a classifier that has low variance. Okay? The solution doesn't change very much. But it probably has high bias because it's not a very good model of the covariance of the data. Let's look now at a slightly more complex model. Now the second model in the middle, so the one with the variances on the diagonal. So now it's not an isotropic covariance anymore, but it's still diagonal, which means it still considers that the features are uncorrelated, right? So it feels basically you have zeros on the diagonal. You're just going to be aligned to your axis. And now again we see, look at the three random draws and how this is being fit by this model. Now you see that there's a bit more variability, okay? And you see the decision boundary now it changes shape quite dramatically. You see this dashed line in the middle, it changes quite dramatically. So this one has a bit less bias than the isotropic model, but it has a bit more variance. And now if we go furthermore completely to the left, that's the full covariance model. So it has, in high dimensional space, this would have tons and tons of parameters. It's basically quadratic in your number of variables. And now you can see, again, random draw D1, D2, D3, so random samplings from this ideal population that we don't know. Now you can see that the decision boundary is basically all over the place. So this classifier is really trigger happy. So it really wants to hug the data. It's probably overfitting in this case, okay? But this has very low bias. It's really hugging your training set pretty well. But the problem is that you see that the decision boundaries are completely different now, right? So you can imagine that if you have some noise in your data, like if you have a new data point that you haven't seen before, your estimates of what class it is are probably going to be very variable in this case. Okay? So that is the bias variance trade-off. Now, I sound like I don't like variance very much, and in some cases it's true, but you have a whole class of machine learning methods in which we actually love variance, and these are called ensemble methods. So things like random forest, for example. A random forest, each tree in the random forest, it's a decision tree, it cuts into the feature space. Each decision tree is very variable, but because we take 500, 1,000, 2,000 of them, we can average them together and then we get better prediction. So in general, variance is not necessarily very good, but if you're doing ensemble methods, typically with trees, then you like to have variance, or instability, as it's called sometimes. Okay. Any questions at this point? Okay. Okay. So that's the principles. Now let's look a bit at practically how we can actually use algorithms to estimate performance. So the first technique is not necessarily used in our field in neuroimaging because we don't have that much data, but I want to show it. I want to show it to you anyway. So as Anil was saying, and this is something you'll hear throughout these talks. This is really, I think, if you take out one thing from this educational course, is you have to be careful about separating your training set and your testing set. So do whatever you want on a training set, but don't touch the test set until you make a prediction. That's really very important. Otherwise, you get double dipping. Okay? So the goal is to predict unseen data. So this means that, one way I like to think about it is maybe in the biomarker case, like if you have a physical biomarker, like a CSF level, like a protein level for something that is diagnostic for some disease, you're not going to change this diagnosis level every time you have a new patient. Maybe, there's some factors to take into account, but basically you're not going to retrain, the thousands and thousands of patients that went through to derive that if you have more than a certain level of tau protein, then you're Alzheimer's, right? You're not going to do that. You have a fixed biomarker, and then you have tables, and then you're going to look at that, and you're not going to re-update. So if you think of this in terms of neuroimaging data, one way of thinking about this train-test separation is basically the same. So you want, let's say you want to build a biomarker. And now I've worked a lot. I have like maybe 100 patients in my model. Now I'm pretty confident that I know where to look in the brain, and that gray matter density here is very diagnosis, let's say, or white matter lesion here is super specific for, let's say, multiple sclerosis. Okay. Now you have a new patient that comes in. You're not going to, probably not, although John Ashburner has some things to say about this, but probably you're not going to retrain your whole model, because the thing is that the person that comes, you don't know the diagnosis label, right? You don't know. So this would be semi-supervised learning. What we're doing here is supervised learning. So you're not allowed to touch the data. All you're allowed to do is have a prediction. And this is exactly the same, so think about the biomarker. It's exactly the same in a training testing scenario. You're training your data. You're not allowed to touch the test data until you're at decision time. Okay, so that's one way to think about it. And this means also that if I have something with neuroimaging, I'm not going to retrain my Dartle template, right, to include this person. And what this means conversely is, if you're really fanatic about this, then you probably need to train your Dartle template only on the training set and not include the test set. Okay? So this is a point up for debate, but you have to think that this strict train-test separation is not only for the classifier, is throughout the whole processing chain. If you're normalizing things, if you're regressing out age, probably you're not allowed to have it on everybody. Probably you should do it only on a training set and then apply these parameters on the test set. Okay, so this is really something. I mean, I'm very fanatic about this, but this is something just to keep in the back of your mind. It's not only when you do the machine learning; it's also the whole processing chain. Everything you do, you have to take this into account. So, with that in mind, here's one technique that we don't really use in machine learning, in neuroimaging, because we don't have that much data. But that's the basics of everything. You split your data, so that means the data itself, the imaging data, and the labels into 3 sets. You would have a training, an evaluation, and a test set. And what you're allowed to do is to play with your training and evaluation set for a little while until you're happy with your error rate. And now you don't touch the classifier anymore. Think again, biomarker. I'm not touching my classifier anymore. And now I'm going to predict the test set. And the results that I'm going to report in the paper are the results on the test set. I can also report the results on the evaluation, but since I've seen it a number of times, I've tuned it maybe 10 times. No, I should change my preprocessing. Okay, I should maybe modulate my VBM data or not. You've done this, but you've seen the accuracy result on the evaluation set. Okay, so this is not very often used because it uses a bit too much data. I'll show you an alternative which is very close to that. But this is also useful to introduce the idea that you, the experimenter, are in this loop. Okay, you're learning. It's not, the machine learning is not only for the machine; it's also for you, right? So when you're tuning your machine or thinking of changing your preprocessing parameter, you're also yourself tuning, contributing your knowledge, and giving it to the algorithm. Okay? And this has, let's say you have 100 subjects, so you would do maybe 30 for training, 30 for evaluation, 30 for testing. The problem is that this, 30 subjects for training is not very much, because now let's imagine you have 50,000 voxels. You have a very high dimensional problem here, because you have 50,000 dimensions, so P is 50,000, and your N is 30. Right? So anytime P is greater than N, then it's called a high dimensional problem. This is really several orders of magnitude. So it's not very favorable to do this kind of thing in neuroimaging. So instead what you do is really a related thing, is basically cross-validation. You've heard Anil talk about it, so I don't want to spend that much time on this thing. But basically you split your data several times. So you do the training set, learn your parameters, tune, do whatever you want, then you evaluate it. Okay, that's fine. But now what you do is you swap your blocks. So you see this little, the colored blocks are moving along. So you rotate your partitions. So what was training becomes testing and vice versa. But what you will report in the end is the aggregate of all these testing blocks, right? All these evaluation blocks. So all the blue blocks here, that gives you an accuracy, or that gives you some statistics every time, and that's what you will report in the end. And then, once you've done this so this gives you one estimate of performance. And then if you're really in a luxurious situation, you will have some tests set aside that you really decided never to touch. That could be a situation, for example, in competitions. And then you will report also this. However, in our case, it's really hard to acquire data. It's very expensive, so we're not really, in computer vision, they don't really care that much about this because they have so much data. It's not a problem. For us, data acquisition is very expensive. So typically what people do is they don't even have this little block test set, right? So they just do this cross-validation over the whole set, and that's what they report, and that's actually perfectly fine. Okay? So Now, Anil also mentioned this, so I'm not going to spend too much time. Now, of course, you know that we've mentioned this little regularization parameter lambda, but you have, depending on the classifier, you have maybe other parameters to tune. Maybe you want to select features. Maybe you want to do a t-test first to see which 10,000 voxels are the best to look at. Well, you're not allowed to do that on the whole data set. Again, you have this idea of train-test separation. You're never allowed to do that. So what you do instead is you split into train and test. And then within the training test, you can do, again, what's called the nested cross-validation. So you do a cross-validation within this, again, only looking at the training set. And this will tell you which 10,000 voxels are the best, or it can tell you which lambda regularization parameter is the best, etc. Okay? So nested cross-validation is mainly used for two things: feature selection and hyperparameter optimization in this case. Okay. So this is many packages now, including Pronto and many others, actually do have this built in, so you don't necessarily need to worry about this. But it's also common that people use, they would use an SVM on NeuroImaging data, and they would not worry about tuning the lambda, but this can change the performance quite dramatically. So this is actually a good idea. It's computationally expensive because you have to run it a bunch of times, but it's a good idea to do that. And the reason I'm allowed to do that is because I only play with a training set. Okay? Within the training set, anything goes. I can do whatever I want. Okay, as long as I don't look at the test set. Okay, and then in some horrible cases, maybe you have nested, but that gets a bit slow. Okay. Okay, so that's the algorithms for estimating performance. But so now I've talked since the beginning about loss, risk, performance, but I haven't actually defined mathematically what I mean. So in this part of the talk, what I want to do is to give you basically tools to compute performance of the classifier, right? So this now, of course, when I say performance, what I mean is always, by default, if I don't mention it, is always on the test set or on a held out test set or in a cross-validation. I mean, of course, on the data left in test fold. So, central to any measure of performance of classification is the confusion matrix, which looks like this. So let's look at the matrix on the right. So omega hat is the prediction of my classifier, is what my classifier think this example is. Let's say my classifier will say this is a patient, class 1, or it's a control, class 0, for example. Okay, so omega 0, omega 1, that's a prediction. And on the left, this is the truth. So it's the actual label. Because we're doing supervised learning, we do have the labels, and we use them to evaluate the performance. The A, B, C, and D are just the counts. So A here is the number of times that indeed the class was omega 0, and my classifier guessed it correctly. The D, on the diagonal still, is the number of times the class was omega 1, and the classifier guessed also omega 1, right? It's just a count of times. If you have 100 subjects, the sum of all these numbers will be 100. So this is just the number of times that this happened over the cross-validation folds. Okay. And of course, the diagonal we want high, and the off-diagonal we want low, because the off-diagonal is the error. So now, based on this, you can compute a bunch of statistics that are very often reported. Class 0 accuracy is just the number of times you got it right over the number of samples from this class. So P0, we can denote it. Class 1 accuracy is the same for class 1. Accuracy overall is diagonal over sum of the whole matrix. And if you have going back to what I was saying at the beginning, if you have the 0-1 loss function, then the accuracy is, that's one way of computing, is just the average loss over your sample. Okay, that's why people use the 0-1 loss, because then it gives you, it's a nice way to compute the performance afterwards. If you're interested about biostatistics, now let's say omega 0, is a healthy person, and omega 1 is a diseased person, so patient. Then sensitivity is, you can again compute from this table, D over C plus D. Specificity, you can compute from this table, etc. So same for positive predictive value, negative predictive value. So basically, this is a table that tells you a lot of things about the classification problem. Two things that are very important. If you see B equals C equals 0, so your off-diagonal is 0 after this, I can almost guarantee that you did something wrong in your processing. That does not happen with real interesting neuroimaging problem. Okay, or I don't know, my algorithms are very bad. But this is really something, it should not be cause for celebration, right? If you see 100% accuracy or 0% error, you should do, damn, I have to do everything again. That's the mindset. Don't be happy about kind of so optimistic things. Or, maybe it's like Haxby data set and it's super easy, but then you're close to that. And then of course, if all your numbers here in this table are the same, then just flip a coin and you'll do just as well as a fancy machine learning classifier. So that's this. One thorny detail here that is still plaguing pattern recognition, and that can happen in neuroimaging because controls are typically easier to acquire than patients, depending on the disease you're talking about. If your classes don't have the same number of examples, typically you have, let's say, 100 patients. Let's not be crazy. You have 20 patients and 40 controls. Okay, so you have a 2-to-1 ratio. Then the classifier, if you don't take special precautions, depending on the classifier, will say, okay, well, I can minimize my loss. I'm just going to say most of the time that it's a control, and that's how I'm going to minimize my error rate. Right? So that's that. If you have a strong imbalance like this, then just the class priors can completely bias your learning results. Right? So what do you do in this case? Well, the common way to do it is just, let's say, again, this example, we have like 20 patients and 40 controls. What you could do is just randomly select 20 controls, kick them out, and have your learning with 20/20. But the problem with this is you lose data. So there's a few other strategies that you can use. You could also use things like called cost-sensitive learning, where you're going to say, well, try to take both classes into account, but that's a problem. The important thing here is if you're reporting results on this kind of data and you have imbalance in your data set, you have to report balanced accuracies as well as normal accuracies. So it's basically the accuracies, but without taking into account this imbalance in the class priors. Okay, so this is basically saying, well, that gives a more complete picture of your classifier. Okay. Now, another way, so far what we've talked about is basically numbers, right? We just said we have correct decisions or wrong decisions, and that's what we have. But internally, many classifiers, including the support vector machine, actually don't just give you +1, -1, or 0 or 1. What they actually give you is some kind of continuous function value. And then, in the case of the SVM, you look at this function value. If the sign is positive, you say class +1. If the sign is negative, you say class -1. So you have a discretization step on top of this. But if you have access to these function values, like you do in the SVM, and you also have this in many other classifiers, then you can actually have a more subtle way of looking at the performance. So I want to show you a little bit about this idea of the soft output of the classifier. So this is an example from real data. This is the classical SPM auditory, the one that you can download, that you've been able to download really forever from the SPM website. Auditory stimulation versus rest. And here we're trying to classify whether that scan is a rest scan or it's an auditory scan. Okay, so here we're doing, in this case, with an SVM. The red curve on the left is the value of the SVM for samples that are tagged rest, so low function value. And the black curve on the right is the distribution of the function values of the classifier for samples that are tagged auditory. Okay, and now what the SVM will do is just put a line through at 0. Whatever is below will be declared rest. Whatever is above will be declared auditory. Okay, but you see that there's quite a lot of overlap. So here, actually, what I want to show you is that depending where you put your decision threshold, okay, you can have very different sensitivities and specificities. And you will see after this that if you increase sensitivity for a classifier, you will decrease the specificity and vice versa for a fixed classifier. So here's how it works. Let's say I put the decision boundary here. So any example that gives me a function value, so a classifier output, a soft classifier output, below, I don't know, minus 0.9 in this case, I will say it's rest. Okay. Now here's what it looks like if you color in. Well, all the guys that are in red here. Let's say this is for some reason the negative class. So all the green part of the curve. This is the true negative. So they were indeed rest, and I classify them as rest. So that's good. Okay. And then if you look at the dark green part on the right, labeled TP, so true positive. These guys were indeed auditory stimulation, and I classify them as auditory stimulation. Okay, but now let's look at the two other colors. So you have the red color on the right side. So these guys were actually coming from the rest distribution, but because I put my threshold there, I say, well, no, they are auditory. So I made a mistake here, right? So these are false positives. And the tiny triangle at the bottom here, Fn, these are the false negatives. Okay, and now you can very clearly see in your mind, I hope that if you shift this vertical line, this blue line along, right, you will basically change the proportion of true negatives, true positive, false negative, false positives. What this means is you will have a spectrum of sensitivity and specificity that you will span with this. One way of plotting such a result, of sliding the threshold, is the famous ROC curve, so receiver operating characteristic curve. In other fields, you also have a logarithmic version of this called the detection error trade-off, which is superior in some ways. But in general, that people use the ROC curve. And so basically, this is the result. You see that it plots sensitivity against 1 minus specificity. So to do this, basically, exactly what it does is just slide this threshold around, right? And that gives you the trade-off. So this is a good idea to have a more complete characterization of your classifier. Okay? And also, you can use it to compare classifiers somehow. So you can see that in most of the regimes, classifier 1 is superior to classifier 2 in this particular case. You can also compute a quantity, another pointwise estimation of classification accuracy called the area under curve. And this is basically, that's what it says, the area under the curve. Okay? And so if this number is higher, it means that over most of the range, this classifier is doing well. So you can think of it as roughly speaking, the proportion, the percentage, or the probability of making a correct decision. That's one simple way of interpreting it. Okay? Again, if your AUC is 1.0, you should be very worried. If it's 0.5, it's right on the diagonal, you should also be very worried, because in both cases, there's probably something wrong with the method. Okay. I want to quickly go over, I'm going to go over one point estimate of regression performance, because the other one is fairly similar. So this was for classification. What if you're doing regression? What if you're trying to, given brain scans, predict, let's say, some clinical score? Well, in this case, you can just compute in one fold. So that's the top here. So the error here, the squared error in this case, is the target. So here we denote it yn. So it's not a label in the sense of class 1, class 2, class 3. Now this is a target. So this could be the MMSE score of a person. So let's say 25. Okay? And f of x of n is the regression. It's again the prediction of the machine learning algorithm. And you just compute the difference between these two square, because we don't care which way the error is, if it's overestimated or underestimated. And that gives you an estimate of the error. And you can average this over all your folds, over all your cross-validation folds. In this case, leave one out, leave one out cross-validation. And then that will give you an estimate of the error. Right? So the mean squared error is just basically the mean of the square of the error, as the name implies. And this will tell you roughly how well you're doing. It's also good to do a few plots. So with the few minutes that I have left, I want to skip this, and I want to talk a little bit about confidence intervals, because this is an interesting subject. Also, if you've seen the paper, what is the title? Exceeding chance by chance, something like that. That's basically what the paper is about. It's complaining that people are not computing confidence intervals and just reporting point-wise, point estimates of accuracy. So let's not do that, and let's compute confidence intervals. So two ways of doing confidence intervals. Again, Anil mentioned a little bit. One way that I like is parametric confidence intervals. It's basically that we assume we know how the accuracies are distributed in this particular case. It has two assumptions that are hard. One is the most important one, as most statistical tests, right? If you do a t-test, you also have these kind of assumptions. The first assumption is that the samples are identically and independently distributed. But because of hemodynamic lag, that's sometimes a problem in neuroimaging studies. So on the little diagram on the right, you can see, for example, that the stimulus, the stimulus is a square wave, but because it's very close together, you have HRF overlap. So one way you could deal with it is to drop scans, as is done in Pronto, for example. Okay, so you have to be careful with this, depending on what your units are that you're trying to test, because in this case you might violate the independence assumption. And the other assumption that's quite important is that the data is normally distributed as usual. Okay, so here, if you assume that this works, then you could do something called the Wilson binomial score test. I just want to show you, so there are implementations of that. If you need code, I can give you code as well. And just look at the last line. I just want to give you an example. I just give you a feel for how wide these confidence intervals are. If you have 60 subjects and you classified 40 of them correctly, so 40 out of 60 correctly, so your point estimate of classification accuracy in this case is 67%. But the confidence interval at 5% significance level, right, confidence, is basically between 50, you could be anywhere between 54% and 77%, right? And these, 60 subjects for neuroimaging is kind of an okay size, but you see that it's, this is okay because I'm still, the lower bound of my confidence interval is still above the chance level, which is 50% in this case for a two-class problem. Okay? But I think this is a very informative way of doing, it's a very informative way of looking at the problem. And really think about this, the confidence intervals are huge because we have very, very small sample size. However, there are problems with this parametric confidence interval, as Anil was mentioning, and indeed you have, sometimes you don't necessarily meet the IID assumption in your data, and so what you can do is a non-parametric version, which is a permutation test. And the way this works is you basically do your analysis once, you get one accuracy, and then you do it a bunch of times, let's say 1,000 times, by randomly shuffling the labels and computing the accuracies. And the reasoning behind this is you want to estimate the null distribution of like what is the chance accuracy that you could get on this data, because maybe there's something you didn't account for. Maybe the correlation structure is so that you can get way above chance just because your data, your experimental design is not necessarily the best for that. So this is a good way of getting a p-value out of your experiments. Okay. And this, I don't have time to go over this comparing classifiers because my 40 minutes are up, but I'd be happy to talk to you in one word. If you want to compare classifiers, don't use a t-test, use a McNamara test, just write this down, and you'll be okay. And I'm happy to talk about the mechanics a little bit about that. Okay, and finally, I want to finish with a reading list, if I have it. Do I have it? I don't have it. Okay, so ask me for the reading list also afterwards. Okay, thank you.